potential doesn't really have a nice analog with gravitational potential energy. It sounds like it's going to be the same thing because it has the word potential in it. But let's just talk about the comparison really quickly, because we got to get that out of the way before somebody thinks that there's an exact analogy that maybe isn't. So we'll talk a little bit about force. So with force due to gravity, we have G m1 m2 over r squared. With gravitational potential energy, we have Eg equals, now we throw in that negative G m1 m2 over r. With electrostatic force, we've talked so far about Coulomb's law, which is Fe equals K Q1 Q2 over r squared, where the K value is specifically, we've talked about it, at least the value we've given is when we were in a vacuum. And of course, the units for force are newtons, regardless of which column we're in. When it comes to electric potential energy, E sub E is K, predictably, KQ1 Q2 over R, not R squared. Now here's the thing. This is electric potential energy. Maybe I should label this out. Electrical potential energy. But I want to make really clear that electrical potential energy, even though it kind of sounds like electrical potential, aren't the same thing. And we'll come back to that in a minute. There's a thing called electrical potential and electrical potential energy. But it's electrical potential energy between two point charges. Things that it's not the same as. Not the same as, I'll even use the epsilon, electric field. Not the same as electric field. Notice that electric potential energy is going to be measured in joules. Electric field intensity was measured in newtons per coulomb. Not the same unit, okay? So electric field, electric potential energy, even though they kind of look like they have E's associated with them, one's actually an epsilon, one's capital E, okay? So that's one thing that's not the same. And we'll talk about electrical potential before we finish out this page, and it's also not the same. These are all things that people kind of get mixed up, I guess, if we don't know what we're talking about or if we just think that the language sounds similar. Anyway, if we move a small charge by a certain distance away from another larger charge, we would need to do work. And this reminds me very much of rockets blasting off from planets. If we were thinking about like that sort of like astrophysics type of thing, only we're trying not to get out of a gravitational potential well, we'd be trying to get out of an electrical potential energy well. So we'd say the work is equal to the change in electrical potential energy. And so that change in electrical potential energy would be energy, electrical potential energy at position, look, we've got RB, so we're going to call that position B, and RA, that would be at position A. And it's charge 2 that's been moved to a further away position. So this is actually charge 1 and charge 2, but at snapshot moment A and then at snapshot moment B. Okay, so this is like an animation. We're seeing what's going on here, okay? So then the change in electrical potential energy would be the difference, EEB minus EEA. EEA. Sounds like something a monkey would say. Anyway, KQ1Q2 over RB minus KQ1Q2 over RA. And if we were going to simplify that out a little bit, a lot of people would write it like this, KQ1 Q2 over 1 over RB minus 1 over RA. You know, as I'm looking at this, a lot of times people will think about it as a linear question. But look, RA is just a magnitude. We're not actually talking about a vector here because energy isn't a vector. Charges aren't magnitudes, or magnitudes. They're not vectors. They don't have direction. K doesn't have a direction. So then I could draw it like this, but I could just as validly draw it like this. Hey, look, if I move a charge from anywhere along that dotted line contour that's at a distance RA away from the other charge, and I move it to any other location along the RB contour, it would take the same amount of work, because we're just talking about a scalar difference here. We're not talking about a vector. And it doesn't even matter if I do some sort of like kinky, weird travel pathway like this one here. I'm just trying to get from position A to position B. It's a contour thing. And this makes me think. It's at least starting to make me think of like if you're on a mountain, we have in geography class. Geography class is famous for these kinds of maps. Where we have like a contour map like this. I know that if I was going to go from this point on this is clearly a mountain, to this point on the mountain, I would have the same change in gravitational potential energy as if I went from this place on the mountain to this place on the mountain. It's a scalar difference, right? And that somehow, like when we're talking about charged particles, people forget about mountains. I want you to remember mountains. It's okay that you'd have the same change in gravitational potential energy between the two dot positions as between the two x positions. Everybody cool with that idea? All right. So I know it's not mountains, but we're trying to hang our hat on old ideas, right? Because sometimes old ideas are helpful analogies for us. So let's just say that it holds true even for nonlinear scenarios. I love this idea of the contour lines and mountain topography as a way of thinking about things. It's a nice way to bring in that multidisciplinary thing. I mean, we've seen these maps, right? Show of hands, how many people have seen a map like that before? Right. So widely seen. This is something that's a part of our collective consciousness. Almost everybody puts their hands up. All right, so let's examine. Let us examine the map of what we know. And if we're going to do a quick examination of the math that we know, I got to do a quick recall. So I want to say recall, equation 1. We said this at the top of the page. F sub E is equal to KQ1 Q2 over R squared. We didn't say it yet on this page, but we've said it previously that epsilon, the electric field intensity, is equal to F divided by Q test. And while I'm talking about Q test, remember once before when we talked about electrostatic force and we tried to make equation 1 and equation 2 play together, we called Q2 the test charge. It's not essential, but it might help us this time with a little bit of algebra. Let's just call the second charge the test charge, just for argument's sake, okay? And then equation 3, what I really want to do is kind of do what we've done before and sub 1 into 2. So we're kind of recapping a workflow that we did once before, and we end up getting epsilon is equal to KQ1 over R squared, R squared. But I want to give myself a little break here. If you're not quite sure of how equation 2 became equations 1 and 2 became equation 3, let's just make sure that we understand what happened there. We just took epsilon is equal to KQ1 Q test divided by R squared. We sub that into the F spot, divide that whole sucker by Q test, and the Q tests cancel out. So I'm just doing this as an aside. That's what happens when equation 1 gets subbed into equation 2, and that's what's going to give rise to equation 3. So just in case you missed that. And then another thing that we could say is something that we put up at the top of the page. I just want to repeat it. This is a capital E. This is not an epsilon. This is a capital E. Electrical potential energy is equal to KQ1 Q2 over R. Okay, electrical potential energy. I'll put a little fluffy bubble around that. But I do want to let Q2 be Q test. Same as I was saying before, you know. Let Q2 be the Q test value. I'll give myself a little bit of a page break up here. And I think I can do a little bit of a figuring here. Yeah, let's do it like this. If I rearrange to get electrical potential energy divided by Q test, in other words, if I take that Q2, here I'll even write it as test again. If I take that Q2 and I bring it over to the denominator on the left-hand side, what I'm going to be left with is KQ1 over R. And I think about what I've got here. Can you guys see that KQ1 over R looks almost like KQ1 over R squared? It's not the same thing, though. Remember that this guy here, electric field, is how much force is experienced per charge. This KQ1 over R is how much energy is possessed per charge. You see the difference? It looks so similar. Oh my gosh, it looks so similar. This guy here has units of newtons per coulomb. This guy over here has units of joules per coulomb. By the way, in electricity, joules per coulomb, it's a dead person's last name, and there's a little info box about this fella right here. And what a name it is. Alessandro Giuseppe Antonio Anastasio Volta, or Volt for short. Okay? So we've got capital V here for volt, and volt is someone's last name, so it stays capitalized. And I'm just going to pause for a second and come back to this.